I mentioned earlier about 2 sections back that in addition to skeletal structures and condensed structures, there is a different way of unambiguously describing chemicals, in particular organic chemicals, and that is to give them unique names. So that's what we're going to begin to talk about in this section. This will probably cover a couple of sections at least. So we're going to talk about how people can name chemicals uniquely, or to name them unambiguously, so that the name tells you exactly what chemical you are talking about. This type of naming is called IUPAC naming. IUPAC is an acronym. It stands for the International Union of Pure and Applied Chemists, or Pure and Applied Chemistry. So this is basically a group of chemists who have come up, among other things, they have come up with a set of rules to follow so that you can give each molecule that you make a unique name, or each molecule that you're working with a unique name that makes it clear and unambiguous as to what molecule you're talking about just when you describe the name. So they make the rules for how to name molecules or chemicals unambiguously. And as an example, we've already seen some of the names. So there's methane, ethane, propane, etc., etc. And at this point, it's probably worth it to have that sheet of paper that points out to you that methane is the alkane with 1 carbon, ethane is the alkane with 2 carbons, etc., etc., because we're going to use that in the next couple of sections. Methane, ethane, propane, these names are actually very old names. They are kept by IUPAC for historical reasons, and they are used a fair amount. The rules that IUPAC has made go far beyond just giving these simple names to simple molecules. The IUPAC naming rules are used more when you deal with more complicated molecules, and you'll see some examples upcoming. So as an example, the idea behind IUPAC naming is that this molecule, even though its simple formula is C4H10, and this molecule, even though its simple formula is also C4H10, they should have different names because the atoms are attached to each other in different ways. And this turns out to be butane, and this, whatever its name is, which we'll talk about later, is something else completely. It is not named butane. So, as far as naming alkanes, one thing to begin with, just as a little bit of a refresher and a little bit of practice, you can pause now, and I would like you to draw hexane. You can refer back to your sheet to see how many carbons hexane has, but I would like you to draw the skeletal structure for hexane. You can pause here, and then I'll talk about it in a moment. This is what hexane should look like, at least in skeletal form. 1 carbon at the end, 2nd carbon here at a corner, 3rd, 4th, 5th, 6th. So hexane has 6 carbons, and every other bond that is invisible but is implied, every other invisible bond is to a hydrogen atom. Now, one thing that I'll point out, this is hexane. This is a cartoon version of hexane. This is also a cartoon version of hexane. It doesn't have to be written from left to right. The line doesn't have to extend left to right. It can go up to down. It can also go diagonally. All of these, this is hexane, and this is also hexane, because the atoms are attached still in the same way, even though I've rotated the molecule. This is also hexane. 1 at the end, 1 carbon at the end, 2, 3, 4, 5, 6. Because even though it's bent, it still has the atoms attached in the same way. So usually you won't see hexane drawn this way. You'll usually see it drawn probably in this way, just because it's sort of more aesthetically pleasing to see it that way. But I'm pointing this out here for a couple of reasons. The main reason is that these molecules aren't rigid. They don't just sit there like a zigzag in real life. These molecules actually can turn and bend, and this chain of carbons, carbon, 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 they can actually bend with respect to each other, and they can turn. So it won't always take on this pretty shape. It could possibly be bent like this, or bent in many other ways. So the key to knowing that this is hexane is to be able to count the number of carbons and figure out how many hydrogens are attached as well. So this is a skeletal version of hexane, so is this, and so is this. Again, another thing that you might want to pause and draw propane. And propane, if you wanted to draw in the most aesthetically pleasing skeletal way, propane has 3 carbons, so 1 at the end, 1 at the corner, 1 at the other end. This is the skeletal version of propane. You could draw it this way. you could draw it like this, which is maybe a little bit uglier, but it is still propane. Again, I just want to emphasize the fact that there are many different ways of drawing these types of molecules, including propane, because you're taking into consideration the fact that these atoms in these molecules, even though they're attached to each other, they can bend and they can rotate. The bonds can bend and rotate. So, we've talked about and we've drawn relatively simple structures for relatively simple alkanes like propane, and eventually you will memorize them. But now we're going to talk about more complicated types of alkanes and how to give them unique names. So here's the introduction to a more complicated type of alkane. This is a cartoon version of propane. Over here, this is an expanded structure. So this is a very detailed structure, 3 carbons that propane has, and you can see all of the hydrogens drawn out and who they're attached to. What we haven't emphasized before, however, is that you can think of propane as being a chain of carbons with hydrogens attached to it. And here's the chain. It's a chain of 3 carbons, one at one end, a carbon in the middle, and then a third carbon at the other end. So you can think of this as a chain of 3 carbons. What's interesting is that once you get to chains of carbons that are 3 carbons or longer, you can actually have the ends. So here's one end that I'm circling, and here's another end that I'm circling. You can have those ends actually attached to each other. You can have this end carbon covalently bond to the other carbon at the other end, and you will end up making a little ring of carbons, a little triangle of carbons, and that's shown here. So now this is not propane anymore. It looks a little bit like propane, but this molecule no longer has an end. If you look at propane, there's an end carbon, there's a middle carbon, and then there's an end carbon. With this thing here, which is almost like propane but isn't, there is no end, because all of the carbons are attached to each other in a little triangle or a little ring. And then there are hydrogens attached as well. Another thing that you'll notice here is that because we attached the 2 end carbons to each other, the only way we could do that and still keep the rules that carbon will always make 4 bonds and hydrogens always make 1 bond is we had to get rid of 2 hydrogen atoms. We had to get rid of 1 hydrogen atom that was attached to this carbon at this end, and we had to get rid of 1 hydrogen atom that was attached to this carbon at this other end. And so you'll see that propane has 1, 2, 3, 4, 5, 6, 7, 8 carbons. This thing here, which is not propane, has only 6 carbons, 2 here, 2 here, and 2 here. So again, just to emphasize, these are not the same thing. They're similar to each other, but they're not the same. So this is an alkane as well, but it's a little bit weirder than propane. And the way that you would draw this particular molecule using a skeletal structure is you would just draw a triangle. And so, it's a little more aesthetically pleasing than drawing the expanded structure, even though these are just cartoon versions of the same type of molecule. The name of this molecule is cyclopropane. So it's almost propane, but you put a little prefix in front of the name propane. Cyclo means that the carbons form a closed ring. So there's no end carbon in this. All the carbons are more or less identical because there's no beginning and no end. And because of that, it has a name that's distinct from propane. It's called cyclopropane. And as I mentioned, you can do this for any of the alkanes that have 3 or more carbons. Down here, I'm going to show you butane. This is the expanded structure for butane. I drew it in a little bit of an ugly way so that the end carbons, this carbon over here and this carbon down here, end up near each other. So I bent the chain, but it's still a chain of 4 carbons. 1 carbon at an end, 2 carbons in the middle, and another carbon at the other end. And the idea is this is butane. However, you can actually get this carbon at the end to connect to this other carbon at the other end. To do that, you have to get rid of 1 hydrogen from this carbon, and you have to get rid of 1 hydrogen from that carbon so that you satisfy the rules. But in the end, you make a different kind of molecule. You make a molecule with 4 carbons in a ring. And this, again, doesn't have an ending carbon and a beginning carbon because they're all in a ring. And so this is butane. I imagine you can take a guess as to what this would be called. You can pause at any point. This is a skeletal representation of this molecule. So this and this are just two different cartoon versions of the same molecule. And as you might guess, since this is called butane, this thing over here, this diamond or the square, is called cyclobutane. So now we're beginning to explore different ways of uniquely naming stranger and stranger alkane molecules. So this is propane, this is cyclopropane, this is butane, this is cyclobutane. So I mentioned this on the previous slide, but basically any alkane that has 3 or more carbons in the chain can be wrapped around to form what's called a cyclic alkane or a cyclical alkane. Cyclic just means that it kind of forms a wheel, or a ring. So this we talked about in the previous slide. This is cyclopropane. This has 4 carbons in the ring, so it's cyclobutane. This has 5 carbons in the ring, 1, 2, 3, 4, 5. So this is called cyclopentane, and you can keep doing this as far up as you're being forced to memorize, which is a chain of 10 carbons. This is called cyclohexane. And again, what I want to emphasize is I want you to be able to name the simple alkanes from 1 to 10 carbons. So methane, ethane, propane, butane, etc. And you should also be able to name the cyclical ones, the ones that form these rings of carbons. So cyclopropane, cyclobutane, etc., etc. And you should be able to recognize them. And again, just as a little bit of a practice exercise, write the skeletal structure for heptane, and you can pause here and then I'll talk about the answer. So heptane has 7 carbons in a chain, so this is the skeletal structure for heptane. Carbon at the end, number 2 carbon, 3, 4, 5, 6, 7. And so that is the skeletal structure for heptane. Here's a different one. Here is a different alkane, a different molecule. What's its name? And you can pause, think about that. And the way to deal with this is to count the number of carbons, and then eventually you'll have these memorized, but 1 carbon at the top, 2, 3, 4, 5, 6, 7, 8, 9. So 9 carbons in the ring. The alkane with 9 carbons is called nonane, and so since this is a cyclical version, since it forms a ring, it should be cyclononane. In the upcoming sections, we are going to talk about stranger and stranger versions of alkanes. So this was the beginning of learning how to learning the rules for how to name different organic molecules and give them their unique names.